Experiment 15, volumetric analysis, total hardness of water by EDTA. Calcium and magnesium salts in water react with soaps to form unwanted precipitates. What we're talking about here is hardness. What is hardness? It is defined in terms of the capacity of cations in the water to replace the sodium and potassium ions in soaps and form sparingly soluble products. In other words, insoluble products. Most multiple charge cations, meaning greater than +1, share this undesirable property. When talking about natural waters, the most abundant cations are calcium and magnesium. Their concentrations generally far exceed that of any other metal ion. Therefore, hardness, for the most part, is expressed in terms of the concentration of calcium and magnesium in the sample, since they're the most abundant. Now, why is hardness important? Well, as a measure of the quality of water for household and industrial use. Hard waters can precipitate calcium carbonate, which can clog filters, pipes, etc. Okay, it can cause many problems. Water hardness is typically determined by an EDTA titration buffered at a pH of 10. Why at a buffer of 10? Because that's the condition for maximum complexing of the calcium and magnesium. So what is EDTA? EDTA is ethylene diamine tetraacetic acid. Okay, there's a 1-to-1 mole ratio between the divalent metal and the EDTA, which is important if you're doing things on a mole-to-mole ratio basis. However, in this experiment, we're going to be using a different concentration expression because it's a little easy to go through that expression to ppms, which is our ultimate goal and what is our measurement for hardness. You can see the structure for EDTA. It's an ethylene, okay, and there's an ethylene, and then there's a diamine, that is your two nitrogen components, okay, and then we have tetraacetic acid, that's our acetic acids, 4 of them. There is an order of stability of metal complexes formed with EDTA. Calcium tends to form a more stable complex with EDTA than magnesium. This means basically that if calcium is present in a water sample, that calcium EDTA complex will form first before any magnesium forms a complex with EDTA present. Well, how will we determine the equivalence point in this titration? We're basically going to take some EDTA and we're going to titrate it with analyte, water solution, or calcium analyte. How are we going to determine that we reached that equivalence point? Well, we're going to use a black tea complex indicator. Okay? And basically, when you have calcium around and it complexes with that black tea, it's going to form a complex that has a dark red color or maroon looking color. When you add the EDTA to that, then that calcium will complex with the EDTA and uncomplex with the black tea. When all the calcium has uncomplexed with the black tea and complex with EDTA, then that black tea indicator would be all that's left, and that's going to tend to have a blue color to it. So we'll be going from a red color to a blue color. Our goal is to basically get that 1 drop difference between that blue, okay, from that red color to that blue color. Basically, we're looking for that lack of any red tint. We're going from a red color solution to a blue, and we're looking for 1 drop difference where you have this red has a slightly reddish tint to it to no red tint. Okay, 1 drop difference if possible. All right, first thing we're going to have to do is standardize our EDTA, and we're going to do that with a primary standard calcium carbonate. Okay, and this calcium carbonate is a primary standard, which means if I stick it in the oven and dry it, if I get way out 1 gram, I have exactly 1 gram of calcium carbonate, which is ideal for standardization procedures. To simplify the calculations with hardness, okay, we use something called the calcium carbonate titer. Okay, and that is put in terms of milligrams of calcium carbonate versus milliliters of EDTA. It's a ratio of the amount of calcium carbonate to the amount of EDTA. So we can use this ratio to determine how much calcium carbonate is in samples by how much EDTA it takes to reach the equivalence point once we have this standardization ratio. This is easier than molarity because in the end we want to get to ppms. That's the scale of hardness is on the ppm scale. Now, one thing to realize is that this is a ratio between two different components. Most units you've done is, moles of some substance per milliliter of the solution, which contains everything. Realize that this is milligrams of calcium carbonate, one unit, one species, calcium carbonate, per milliliter of EDTA. So you have to put the units, okay? When you write this, you have to write the units of calcium carbonate in EDTA. It's not a solution. This is a ratio of two different numbers that will put together in the titer. Okay, so you have to put the calcium carbonate and you have to put the EDTA to tell the reader that it is milliliters of EDTA and milligrams of calcium carbonate. After EDTA is standardized, we can use that ratio to determine the hardness of the water sample by titrating it with EDTA and using the calcium carbonate titer. So once I have this ratio, this standardization ratio, then I can do any sample, any unknown, see how many milliliters of EDTA it takes to get to the endpoint, multiply it times this titer, and I have to find out how many milligrams of calcium carbonate is there, and then go from there to ppms. Total hardness is typically reported in ppms of calcium carbonate. That's parts per million. So how do we get from the titer to the parts per million? Well, ppms of calcium carbonate is milligrams of calcium carbonate per liter of water sample. So your goal in trying to get to ppms is to figure out how many milligrams of calcium carbonate is there per liter of water sample you're analyzing. One thing to keep in mind, if we're dealing this with aqueous solutions, that typically 1 ppm is equivalent to 1 milligrams per liter because the density of water is 1 milligram per liter. Okay, so aqueous solutions, a ppm is equivalent to a milligram per liter. So how are we going to do the standardization procedure? Well, we will start the experiment on page 104 at the second paragraph of standardization. We're going to skip the blank run. It's not necessary. We're not going to do the blank. Okay, we can easily determine and see that one drop difference. So we're going to skip that first paragraph and go straight to the second paragraph. There's some changes in that second paragraph. We're going to use the following measurements. We're changing the recipe of this experiment. We're going to use 10 milliliters of the 0.01000 molarity calcium carbonate. Okay, that is your standardized calcium carbonate that will be in the lab. It's already standardized. On the bottle will be its concentration. That is what you use, that concentration, to do your calculations, instead of the 25. Okay, so we're cutting it back. Okay, we're just doing 10 milliliters instead of 25 milliliters. We're cutting back the pH of your pH 10 buffer. We're using 2 milliliters instead of 5. Okay, deionized water, we're cutting that back as well. We're using 10 milliliters of DI water. And in the black tea indicator, we're using 4 to 6 drops. Note in the lab procedure, they say to add it later when you get close to the endpoint. Let's not worry about that. We'll add the indicator from the start. Okay, so you go ahead and you have your sample ready to go and do your titration until it changes from red to blue. Okay, so we add our black indicator from the beginning of the experiment. We're going to try to do our experiment and get the first run to be a good run. Okay, the lab manual says to kind of go quickly on the first one. We want to go slowly on the first one. We want to make sure that we get a good reading from the first one as well as the second and third one. Okay, so you want to creep up on the first one, slowly adding volume to the analyte until you get that color change. And then on the second and third one, you know the endpoint is you can go a lot faster. You can add a lot to it till you get about a milliliter or two from where the other one was, and then slowly creep up onto that change. In this experiment, for the titration, the standardization, we want to do a minimum of 3 runs. We want good precision. Okay, you want to do it till you get good precision. That's probably about plus or minus 0.1 milliliters of EDTA getting to that color change, that 1 drop difference. Okay, so you're looking for about 3 good runs within about 0.1 milliliters from that color change. In the report, our goal for the standardization, okay, this is our goal for the standardization, Okay, goal for the standardization is we want an average titer plus or minus the standard deviation of milligrams of calcium carbonate per milliliter of EDTA. And we're looking for that because we're going to use this value to calculate our unknown water. Just to give you an idea of the endpoint, so that you can get a good run on that first one, the endpoint should be approximately between 8 and 12 milliliters. So you probably want to do the first run, you can add quickly to about 6 or 7, then slow down to figure out where that actual endpoint is, and then on the second and third one, you can go a lot faster. Okay, let's talk about the standardization calculation. Our goal is to get milligrams of calcium carbonate per milliliter of EDTA. That is that titer we want. Okay, it's a ratio of milligrams of calcium carbonate for every milliliter of EDTA that is titrated to reach that equivalence point. So we start off, we know the concentration of our calcium carbonate. That will be on the bottle. Okay, it's going to tell you whatever that concentration is. Be 3, 4, 6 figs, whatever's on the bottle, that is what you're going to use. Okay, we basically want to get to milligrams of calcium carbonate. So how can I get from moles of calcium carbonate to milligrams of calcium carbonate? Well, I'm going to have to figure out how many moles I actually have, and then from moles I can go to molar mass, etc. So I know that I have 0.0100 moles of calcium carbonate for every 1 liter of solution. Well, we're not titrating a liter of calcium carbonate. We're only using 10 milliliters. So the next step would be to use our 10 milliliters, okay, multiply by our volumes. So what happens is I'll multiply volume times molarity, I get moles. Now notice that I left it in milliliters for this particular calculation. That milli is really a prefix. It's just a power of 10. The actual unit is liters. So I want to get to milligrams, so I'm going to go ahead and leave that milli there and cancel out the liters, but I'm leaving the milli there. Okay, that's just a power of 10. Now, alternatively, what you could have done is converted that into liters by dividing by 1,000. That's up to you. Okay, but my goal is to get to milli. So if I do that, I'm going to end up having to convert it back to milli later, which means I'm going to have to multiply by 1,000. So I'll do it this way, where I'm just canceling the liters and leaving the milli. So in essence, if I multiply 0.0100 times 10, right now what I have is millimoles. That milli now is just part of that moles. Okay, I just canceled the liters. So now I want to get from millimoles to grams, milligrams. So the next step would be to use your molar mass. The molar mass of calcium carbonate is 100.09 grams of calcium carbonate for every mole of calcium carbonate. So what happens now is my moles cancel. Okay. So now I'm left with milli again. And I have my gram. Okay. So if I do 0.0100 times 10 times 100.09, what I'm making is milligrams. I got milligrams of calcium carbonate. That gives me my numerator value. Now I just need my denominator, which is milliliters EDTA. So all I got to do is divide now by the volume it took to get to the equivalence point, to get that color change from red to blue. So then I have my milliliters of EDTA now coming in from dividing the whole expression by that milliliters of EDTA, which gets me my final answer, which is my milligrams of calcium carbonate per milliliter of EDTA. So this is basically your calculation. The only variable you have in this for each run of your standardization, okay, all this would be the same. All the front part here is the same. That doesn't change. Okay, where your variable is going to be is right here with your milliliters of EDTA. Each run you have a different volume. Theoretically should be exactly the same volume, but there would be some error in your analysis. And you calculate your titer, and you're going to want to get 3 of those that are very precise. Okay, probably looking at getting some results within plus or minus 0.1 milliliters to have some real good precision on that experiment. One thing I want to note, okay, that we're not calculating molarity of EDTA, even though the manual says to. We're not requiring it. We're going to do everything as our titer and calculate our ppms. We're not worrying about molarity in this experiment. Next, we'll do the unknown water titration. We're going to do this experiment just like it's written, except we're going to add the indicator from the start and try to make that first run count. Okay, don't do it rapidly. Do it slowly till you know where that endpoint is, and then you can go faster on the next couple of runs. Okay, so exactly the same, except we're going to go ahead and add indicator from the very beginning. Once again, we're going to do a minimum of 3 runs. You want good precision. Make sure you do it till you get good precision. Okay, just to warn you, give you an idea, to give you a hint for getting the first one to count. The unknown endpoint is going to be approximately 5 to 12 mils. So I would go the first run, go about 3 or 4, slow down, see where you get that endpoint, and say it goes to 10. Then on the second run, you can add about 8 and then slowly get to it. That way you can do the other ones a little quicker. Goal in this experiment. Okay, goal for the unknown. Okay, the goal for the unknown is an average ppm plus or minus the standard deviation of ppm of calcium carbonate of the unknown water sample. Remember, when we're talking ppms, what we're talking about is milligrams of calcium carbonate per liter of water sample. Also, we must report based on the water hardness scale the classification of your unknown water sample. So I want you to get your final answer, your average ppm, and then on the water hardness scale, tell me what type of water it is. Is it soft? Is it slightly hard? Is it mildly hard? Is it hard? Very hard. Okay, so you need to report your average ppm. What is it on the hardness scale? So to find that, you're going to have to go do a search. You can find it on the internet. Okay, find the scale. I want you also to write the scale in your report and your discussion. Tell me what the scale is. Tell me how many ppms you need to be classified as soft. How many ppms to be classified as slightly hard. Give me the scale in the discussion somewhere, and then tell me what is your water, unknown water, classified as. Now, how do you do the calculation for the unknown water? Okay, our goal here is ppms of calcium carbonate, which is milligrams of calcium carbonate per liter of water sample. So you did your standardization, so we start off with our titer. We know we have some average titer milligrams of calcium carbonate per milliliter of EDTA. Our goal here is now to get our milligrams of calcium carbonate per liter of water sample. Well, we know from this ratio that I have my average titer milligrams per every 1 milliliter of EDTA. Well, it took so many milliliters of EDTA to get to that endpoint to change that red to blue color. So the next step will be to multiply by my volume of EDTA to get to that equivalence point. Okay, so what happens there is my milliliters of EDTA cancels. Okay, so now I know how many milligrams of calcium carbonate I have in that whole sample now. Okay, by multiplying it, so I have my numerator. Now, I want that per amount of water. Well, all I got to do then is divide by my size of my water sample, which in our experiment is a 50 milliliters, so we convert that to liters to get it to correct units. So 1 divided by my liters, so now I have my liters of water coming from there, and I have my milligrams of calcium carbonate coming from that calculation, which then gives me my total milligrams of calcium carbonate per liter of water. And we realize that 1 ppm is equivalent to a milligram per liter of water, so therefore that is telling me my ppms of calcium carbonate. Now, we could have done this on a molarity scale, knowing it's a 1-to-1 mole ratio, but we're not going to do that. I'm going to keep this on the titer scale because of the fact that we're doing the hardness, which is on the ppm scale. So do not worry about any of the molarity calculations. Now, how much chemicals do you need to do this experiment? Well, basically each group only needs the following. Okay, EDTA, you need about 150 milliliters. Your pH buffer, you need about 40 mils. Now, keep that under the hood. It kind of has a smell to it, so you might want to keep that under the hood with a beaker with your initials on it and use it as you need it. 0.01 molarity of calcium carbonate standard solution, you need about 50 mils. And your unknown water sample is 200, which TA will assign you an unknown water sample. There's an additional question for this lab experiment. So once you finish the lab report, write in your discussion, I want one more page where you put the additional question and give me the answer. Additional questions as follow. Hard water is a major issue in which science is used to solve the problem. After your conclusions in your Experiment 15 lab report, you will discuss another major issue in which science is involved. Climate change is thought to be accelerated by carbon dioxide from coal and natural gas fuel power plants. Due to the increasing need for electricity, other power sources will be required to lessen the emissions from fossil fuels. List 3 possible alternative sources for the production of electricity. So you need to list 3 possible alternative sources. For 2 of your responses, describe an advantage and a disadvantage between it and the current coal and natural gas power plants. So for 2 of those responses, I want an advantage and a disadvantage between it and the current coal and natural gas. You're going to put that all at the end of your lab report. So after you finish your lab report, discussion, conclusion, after the conclusion, I want you to put additional question and give me that information. It's important. This is going to be graded in your lab report. If you don't put it, you're going to be missing points. So I want this in your lab report.